Okay, so good afternoon everyone. I'm Simon Graham. I'm a PhD student within the Tissue Image Analytics Lab here at the University of Warwick, and today I'll be presenting my work on Rota-Net, rotation equivariant networks for Gland and Lumen segmentation. And this work was done jointly between myself, Professor David Epstein and Professor Nasir Rajput. To outline the talk, I'll first discuss automated gland and lumen segmentation, and then discuss rotational symmetry within histology images, and then discuss the method of Rota-Net, and then conclude with the results and the summary. So gland and lumen segmentation, it's a vital prerequisite step if we want to then subsequently extract any features, such as the shape, size, and textural features. And we've recently shown within our lab that features such as the morphological features can be indicative of the grade of cancer. In addition, the lumen can also provide diagnostic cues. Now, the challenges with gland segmentation include separating clustered glands, as we can see by the green boxes here. Then, with increasing grade, the glands display an increasing variability in the shape and the size. So therefore, automatic methods may struggle to actually segment the glands and the lumen. Now, current state of the art is achieved by convolutional neural networks, and part of the reason why they achieve such a good performance is because they exploit the translational symmetry inherent within the histology images. And by this we mean that no matter where a subcomponent of an image is within that image, it should not matter at all. And so therefore, the design of the CNN means that the kernel translates over the receptive field, and therefore the filter response will be the same no matter where a part of an image is within that image. Now, to dig into the idea of symmetry, we can see two objects here, which we may recognize. The Batman logo has a clear mirror symmetry with a vertical line of symmetry going down the middle, and then the object on the right-hand side displays rotational symmetry of order 3. So by definition, a symmetry of an object is a transformation that leaves that object invariant. But in machine learning, we are specifically interested in the symmetries of the labels. So what transformations will leave the label of that object the same? Now, just moving on a slight bit, symmetry groups are essentially a set of transformations where each transformation is also a symmetry. For example, we have here two symmetry groups, so the cyclic symmetry group of order 4 and the cyclic symmetry group of order 6. And we can see here, shown by the Cayley diagrams, if we look at the C4 group, each arrow shows a transformation. Here, a rotation by a multiple of 90 degrees, and it's still a square. So we say that this object is symmetric. Now, the next statement that I wanted to make is the fact that histology images are symmetric under rotation. So, for example, if we extract an image patch from a WSI, no matter whether we rotate it by 90 degrees, 180 degrees, or 270 degrees, it still has the exact same information content. Further to this, if we look at all the different orientations of these image patches, the important thing about histology is the fact that all of these different image patches at the various orientations are equally as likely to appear. So this is different to natural images and even other medical images, where if we rotate those images, we still might be able to recognize what they are, but they are not likely at all to be appearing in this orientation. So the question is, how do we build in this prior knowledge of rotational symmetry inherent within histology images into our current models? And how we do this is we need our methods or our models to be rotation or equivariant to rotation. So to give an idea of what equivariant means, I'm going to show an animation on the next slide. And essentially, it means that if an image is transformed, then the filter responses should also transform in proportion to the input image. Moment of truth. Yeah, that's what I'm doing. Okay, there we go, eventually. So we can see here that the image on the left is translating, and the filter responses are translating in proportion to the input image. And therefore, the window showed that the predictions were stable. Whereas when the input image is rotated, we can see that, if you can see, there's an instability here with the motion compensated window. And this is because the filter responses do not respond in proportion to the transformation of the input image. And this animation, by the way, is from a recent work on harmonic networks published at CVPR in 2017. Okay, so to put that diagrammatically, if we transform an image patch by, in this case, a rotation multiple of 90 degrees, and we send each image patch through a network, then for this to be an equivariant representation, we should know what this transformation is here. So in other words, the transformation of the filter responses should transform in proportion to the transformation of the input image. So you may have heard of invariance. Now, invariance is a specific case of equivariance where instead the second transformation is the identity function. So in other words, the mapping is independent of the transformation. Now, data augmentation has been used very widely to achieve invariance. So because we're talking about rotation, introducing various rotated images into the network will achieve rotation invariance. But this requires any network to learn the filters at various orientations. And the mapping is independent of the transformation. So, as I said, because these filters need to be learned at various orientations, the models are prone to overfitting. Whereas when a network or a model is equivariant, this means that the filters can be reused at various orientations and allows the network to have more of an expressive capacity and learn more discriminative features. So we use a combination of both, because even when you have an equivariant representation, if you use a symmetry group that is a larger group than the symmetry group that you're incorporating within your model, then there is a significant gain from using both. So how do we use, or how do we make our network to be rotation equivariant? And we use the approach that was used by Taco Cohen and Max Welling at ICML in 2016 from the University of Amsterdam. And so to display this, we have an animation. So this here shows the orientation of the kernel, and a normal planar convolution that most of you will know will introduce the translation of the kernel across the receptive field to get the feature map on the right-hand side. Now, this exploits the translation symmetry within the image, but we don't need to just limit the kernel to the translation. We can also rotate the kernel and then do the same planar convolution. We can rotate it again, and we will get a feature map for every orientation. So here we have not just one feature map for a given kernel, but we have 4 feature maps, one for every orientation. And the interesting thing about the G-convolution is that we can see that the feature maps don't only just rotate with the input image, but they also cycle. And the important thing to see here is that we effectively know the transformation of the G-convolution. And so therefore, we have learned an equivariant representation. So now these G-convolutions can be stacked to make the network equivariant to rotation, as long as we do some other tricks, such as convert batch normalization to a rotation equivariant equivalent, where we aggregate the moments per group. Non-linearity doesn't need to be changed. And then at the end, we use a projection layer. So we will have, near the end of the network, the 4 orientations still, and so therefore we will average over each orientation. and this actually achieves invariance at the output of the network. So this shows the overall network of Rota-Net, where it's pretty much a U-Net style network, but we split the branches at the output of the network as we reach the highest resolution, where one branch achieves gland segmentation and one branch achieves lumen segmentation. And all we do here is we replace all of the convolutional operations with the G convolution. And then here is the projection layer, so we average over the orientations here to then go to the gland prediction and the lumen prediction. And we also use a multi-class strategy, so we incorporate the contour to help separate glands in close proximity, which is a key challenge, as I mentioned in the first slides. Now, the data set that we used was the glass challenge data set. That can be actually seen by scanning this QR code, and it consists of 165 H&E images of 20 X magnification, where we have 85 training images and 80 test images. And we also have exhaustive gland and lumen annotation. So for the glass data set, you'll see that the gland annotation is online, but at the moment we haven't released the lumen annotation. To show the results, we compare our method with MildNet and also some other existing methods, and we achieve state-of-the-art performance. This just shows here at the moment the gland segmentation performance. And then on the next slide, we compare Rota-Net to a U-Net and FCN8, where we convert these approaches to do the same sort of thing. And by that I mean that we have a multi-branch strategy where we have one branch achieving lumen segmentation and one branch achieving gland segmentation. So here as well we achieve state-of-the-art performance compared to these methods. And the last thing that I wanted to show, so the difference here between these two models is the number of classes. So here we incorporate the contour and here we don't incorporate the contour. The baseline method is simply the same network, but it's not rotation equivariant. So it's just the same method, but using planar convolution the whole way through, and normal batch normalization. And how we make sure the number of parameters are the same is, compared to the baseline, in the rotation equivariant networks, we reduce the number of filters by a factor of 2 at every layer, and that maintains the number of parameters to be the same. Well, there or thereabouts. So some visual results. We have the comparison of the ground truth and the proposed method, where the yellow boundaries show the gland boundaries and the green boundaries show the lumen. So as we can see, we get some nice results, and our method picks up some of the lumen which have not been annotated in the ground truth. So to conclude, histology images are inherently symmetric under rotation and can be exploited within our proposed framework of Rota-Net. And this is just hopefully the start of exploring these kind of methods, but it motivates the use of future rotation equivariant methods within histology image analysis. So to conclude, I'd like to thank all of the members of the TIA lab here at Warwick, in particular my supervisor, Nasir Rajput, also my funding governing bodies, MRC and EPSRC, and thank you to everyone for listening.
Thank you very much. We have time for just only one question. Right, I have a question. So can you comment on the running time of Rota-Net as compared to the network that...
Yeah, so that is at the moment the thing that we want to try and improve next. So compared to the baseline methods, Rota-Net takes longer to process the images, around 4 times as long as you can expect. So this is a limitation of the method. So the question is, how do we combat that in the future?